The second approach to solve the contact problem is to add a constraint equation, and this is the so-called Lagrange multiplier method. On this slide, we are going to demonstrate the Lagrange multiplier method for stick conditions, which means that no separation between the contact surface, no sliding, starting from the total potential energy. So on the top, we have the expression of the waveform, or the principle of virtual work, including the contribution from the contact stresses. This is a condition for a stick. It's basically the gap, which is now a vector, is 0 for both the normal direction as well as for the tangential direction under contact. And again, small x is equals to capital X plus u. U is our displacement. Now this is the condition for stick and slip. We have the non-dimensional parameter tau. When tau is between -1 to 1, we have a stick condition. So this slide is talking about this condition. Starting from the total potential energy of the system, we have n bodies. So the total potential energy would be the sum of the internal energy and the potential energy from external work of all the n bodies. So this should be a complete bracket here. Now with the Lagrange multiplier, we have a constraint total potential energy to minimize, which means that now on the right side we have minus over integral over the Lagrange multiplier, which in this case would be our contact stresses, dot product with our vector constraint equation. When the constraint equation is satisfied, this term goes to 0. When we try to minimize this functional, we can take the variation of this functional and set it to 0. And we apply the variation on each of these terms. So the first term, the variation of the internal energy, would correspond to the first term on the left of our principle of virtual work. So this is the virtual work done by the Cauchy stress tau with respect to a variation of the strain. And then we can perform the variation on the principle on the potential of the external force. So this would be the minus of the integral on the virtual work done by the body force and externally applied traction on the surface of the bodies. So note that there is an inverse relationship between potential and work. So basically, when the external force is doing positive work, the potential of this force is decreasing. So imagine the case of a ball falling. The weight of the ball is doing positive work when the ball is falling from a higher position, and then the potential of the ball is decreasing. Now, there is an additional term that we need to perform variation on, which is this term. And when we perform the variation, it would then contain two terms. One is that we keep the constraint constant and then apply the variation on Tc. The second term is that we keep Tc constant, then apply the variation on the constraint. And then this would give us two terms. This term, if we analyze further and plug in the expression that small x equals to capital X plus u, where capital X is the initial coordinate, which doesn't vary, then we get this expression. So basically the variation performed on capital X is equivalent to performing variation on the displacement. So this is exactly this expression. And if we look at these two, this expression is exactly the expression here on the left. This expression is exactly this expression here. And this one is the one that is expressed here. So when we do the variation of this constraint functional, we have retrieved this equation together with this additional one. And this additional one is called the weak form of constraint equation. So this is a strong form which says that this equation needs to be 0 on gamma c. And this is the weak form, which means that this equation, dot product with arbitrary variation of surface traction vector integrated on over gamma c, needs to be 0. And the two are mathematically equivalent. Now we have two equations. after minimizing the constraint functional using Lagrange multiplier method. The first equation is our usual wake form, which is the principle of virtual work. The second equation is the wake form of the constraint equation. And eventually, we solve for both u and tc, because both of them are independent unknowns. And they both need to be interpolated, and eventually we can arrive at the system equation and solve for them simultaneously. And in this method, the constraint is exactly enforced. So there is no overclosure interpenetration, there is no penalty stiffness, but we have a much larger system of equation to solve, so it's more costly than the penalty formulation. So this is for the stick conditions. While in the tangential direction, we also have a steep situation when the absolute value of tau equals to 1. And for this, we need to modify the constraint equation and correspondingly the wake form of it, because now we are only enforcing the normal direction of it. So we first decompose our Tc equals to into the normal and tangential components, and then we modify the constraint equation. So now it only enforces on the normal direction to be 0 when there is a contact on gamma c. And the wake form of it is that this equation needs to be satisfied when it multiplies with arbitrary variation of the normal traction integrated on gamma c equals to 0. And if you look at this form, it is not the symmetric form of this term, which means that when you look at the stick condition, this form, the term in the integral, and this term in the integral here for the wake form of the constraint equation, they are symmetric, because variation of u1 is the same as variation of x1, because the capital X doesn't vary. So I can effectively replace u here with small x, and then variation of x1 minus variation of x2 dot product with tc is symmetric as compared to x1 minus x2 dot product with variation of tc. So when you perform the linearization and derive the tangent stiffness matrix, you need to take the partial derivatives of these terms with respect to u and tc. And when you have such symmetric forms, you would end up having a symmetric tangent stiffness matrix. But in the case of sleep, these two forms are non-symmetric. Here you have the contribution from both normal and tangential directions, and here you are only enforcing on the normal direction. So in terms of forms, they are not symmetric. And the eventual consequence of this is that you do not have a symmetric stiffness matrix. And of course, in this case, your Ts is no longer an unknown because it's directly related to Tn. So you eventually are solving u and Tn only. So the tangent stiffness matrix is not symmetric. And as friction, we are talking about friction. Friction is a path-dependent force, which means that it's not conservative. By conservative, I mean that the work of the force does not depend on the path, such as the weight. Weight is a typical example of a conservative force. So the work of the force only depends on the initial and ending positions, while friction is a non-conservative one.